This video introduces the concept of kappa and why it should not be used as a method of validation. This video was created by Smetha Bitar, Nada Haddad, Emily Heltzel, and Medina Khadiatova. The kappa statistic is widely used as a method of validating land change models. However, kappa is a faulty index of agreement, and many scientists misinterpret the statistic. Quantity and allocation disagreement are more helpful measures to determine how well a model performs. Further, any two-map comparison is a flawed method of model validation. A three-map comparison with misses, hits, wrong hits, and false alarms is the best method for validation. The figure shown here demonstrates a reference grid and two comparison grids. Ask yourself which comparison grid disagrees more with the reference grid. At first glance, it appears that comparison 1 disagrees more, or is more different from the reference grid than comparison 2. The methods of quantity and allocation disagreement would agree that comparison 1 disagrees more. Comparison 1 has 14 out of 16 pixels that are different, which equals an 87.5% difference. The wrong quantity for red and green pixels is what causes this disagreement. Comparison 2 has only 2 out of 16 that are different, which equals a 12.5% difference. The wrong allocation of the red and green pixels is the main reason for this disagreement. The kappa statistic tells a very different story. Comparison 1's kappa value is 0.01, while comparison 2's kappa value is negative 0.07. This suggests that the comparison 1 grid is more similar to the reference grid and therefore more accurate, something we know is not true from the previous slides. Let's take a look at how those kappa values were calculated. The kappa equation is calculated as P agree minus P chance divided by 1 minus P chance. P agree is the probability of agreement. P chance is the probability of random agreement. P agree for comparison 1 is 2 divided by 16, as 2 out of the 16 pixels agree with the reference grid. P agree for comparison 2 is 14 divided by 16, as 14 out of the 16 pixels agree with the reference grid. This is a similar method we saw in slide 4 with the quantity and allocation disagreement. P chance is where a randomness element is introduced to the kappa statistic. Further, we get a negative kappa for comparison 2 because the actual agreement between pixels is less than the random agreement kappa has calculated. Ideally, the probability of each pixel being red or green should be 0.5 or 50%. If we use 0.5 as P chance instead, we will also get a negative kappa. This clearly shows that using randomness or chance in the kappa statistic does not make sense. Land change patterns are far from random, so using randomness as a baseline for map comparison and thus validation is inappropriate. Kappa cannot accurately express how well a land change model is performing. The purpose of kappa is to compare a simulated map's accuracy relative to the expected accuracy of the actual land use map. Essentially, kappa is used for accuracy assessment. It is calculated based on a stochastic model of random allocation, and it measures how far from random a simulated map is. Depending on which kappa equation is used, the scale will differ. Typically, kappa values range from -1 to +1, with +1 indicating perfect agreement, 0 indicating the map agreement is the same as random, and -1 indicating no agreement. Kappa summarizes the correlation of agreement between the simulated map and the random allocation. This leads us into the limitations of the kappa statistic. To start, randomness is a misleading baseline. It is important for sampling, but simulations and classifications are based on selected parameters, not random sampling. Therefore, it does not make sense to compare accuracy to randomness. Secondly, the kappa index is a ratio. This causes problems in the calculation. If the denominator is 0, then the kappa statistic is undefined. In addition, the ratio is hard to interpret because it is unclear if a large or small ratio derives from the numerator or the denominator, making it difficult to improve the accuracy of the model. Furthermore, the results of the Kappa statistic may be inflated for simulations where minimum change takes place over time. Lastly, the use of a single summary statistic for accuracy assessment makes it very challenging to improve the model solely from a single aggregate value. There are more components to accuracy and error than one summary statistic, which Kappa fails to illustrate. Three-way map overlay validation is the most holistic method to evaluate a model's accuracy. Land change models are complex, and as a result, they require more information beyond one summary statistic to determine its accuracy. A cross-tabulation of 3 maps is required to validate the land change simulation. These include a reference map from time 1, a reference map from time 2, and a simulated map from time 2. In the figure below from Varga and al., a cross-classification of the reference, simulated, and actual map are used to produce a validation output that reveals where the model generated hits, misses, false alarms, wrong hits, and correct rejections, allowing the land change modeler to validate the output of the land change simulation. The quantity and allocation of misses, hits, false alarms, and correct rejections is more telling than the aggregate statistic of the Kappa value. These results indicate where and how the model went wrong and can be improved. This figure shows a visual representation of misses, hits, wrong hits, and false alarms for a land change model simulation from the previous map shown. There exist many alternatives to Kappa for accuracy assessments of simulations and classifications. The figure of merit statistic summarizes actual change over the total change in a simulation model by calculating hits divided by the sum of hits, misses, and false alarms. Quantity disagreement can be used to understand how many pixels were wrongly projected. This is calculated as the absolute value of false alarms minus misses. Allocation disagreement is important for understanding how the model misallocated change. Finally, total disagreement can be used to understand both allocation and quantity disagreement as a single value. Total disagreement is calculated as the sum of quantity disagreement, allocation disagreement, and wrong hits. For more information on the faults of the Kappa statistic and alternatives to it, please refer to the references displayed on this slide. When it comes to land change modeling and many other professions, Kappa addresses a question that is usually irrelevant. How close or far something is from random is not a good metric for determining how accurate it is. Instead, scientists should focus on quantity and allocation disagreement. Kappa is not an appropriate method for evaluating a land change model's accuracy. Validating a land change model requires a 3-map comparison. A thorough video detailing the methods of land change model validation can be found at this link.